Welcome back to the lectures in chemistry and the atomic structure and chemical bonding. My name is Mangala Sundar. I am in the Department of Chemistry, IIT Madras, and my email addresses are given here. The coordinates are here for you to communicate to me. The lecture continues from what I left in the previous one, the properties of spin angular momentum. We saw in the previous lecture the spin a half angular momentum, and we looked at the Pauli spin matrices. The relation that we have with the Pauli spin matrices, the commutation relation and the anti-commutation relations, all those things were explained a bit. And in this lecture we continue with the same, but now with integer angular momenta and higher angular momenta, namely not spin a half systems, but spin 1, spin 3 halves, a little bit of that before we proceed to the understanding of the interactions between two spin a half systems. In this course, of course, the importance is to the interaction between two electrons or two angular momenta of two spin 1 half systems. Let me first restate or recall what we wrote down in the last couple of minutes of the last lecture. We did sigma x, sigma y plus sigma y, sigma x Pauli spin matrices, spin 1 half matrices. That is equal to 0, and likewise for sigma y, sigma z plus sigma z, sigma y, and sigma z, sigma x plus sigma x, sigma z is equal to 0. And then we had sigma square as sigma x square plus sigma y square plus sigma z square, and that is 3 times the identity matrix 2 by 2. But recall that when we wrote down the spin angular momentum operator Ix, we had it as 1 by 2 0 1 1 0, and therefore this was written as 1 by 2 sigma. Okay. Therefore, if you are looking at I square, then essentially it is 1 by 4 sigma square. Therefore, it is 3 by 4 into the identity matrix 2 by 2, namely 1 0 0 1. This is the spin a half angular momentum. This is the Pauli representation of the angular momentum spin a half in terms of matrices. The relation between the two is given by this numerical factor 1/2. I think that is important to remember. Now, also recall the properties that when we wrote down I plus on beta, we had it as alpha, and I minus on alpha is equal to beta. Okay. These things can be generalized. The angular momentum properties of I plus and I minus on any spin angular momentum states can be generalized to the following relations. Recall that when we wrote down alpha as a state, it was the quantum numbers half and half corresponding to the I squared on alpha or beta, giving you half into half plus 1, which is what was written as 3 by 4 times alpha times beta and Iz on alpha and beta. This is just to recall so that we continue from here. You remember this was a 1/2 on alpha, and this was a minus 1/2 on beta. Okay. Now, the general relations for all these things is I for 1, 3 by 2, 2, 5 by 2, 3, and so on. These are all important in the coupling between the angular momenta as well as nuclear spins when we study at some point of time later the nuclear magnetic resonance spins as well. but the properties of the angular momentum are all the same and they are generalized by the following relations, namely Iz on the spin state I m, the two values, the quantum numbers are given as Im, this is given as I into I plus 1 Im, and Iz on m, again sorry, Im is given as m times Im, and the number of states Im for any given I is 2i plus 1, 2i plus 1. Therefore, if you think about a spin 1, the I here corresponds to this quantum number, the m here corresponds to this quantum number, because this is I square, I am sorry, this is not Iz, this is I square. The I square and Iz being the operators which commute among themselves, only two quantum numbers describe the spin state of a single spin, and these two quantum numbers basically are used to represent the state Im. Therefore, for a spin 1, we have I is equal to 1 and m is equal to 1, 0 and minus 1. So, we have three states 1, 1, 1, 0 and 1 minus 1 with the corresponding values for the Iz operator. That Iz on 1, 1 gives you 1 times that, Iz on 1, 0 is 0, Iz on 1 minus 1 gives you minus 1, and I square gives you 2. Now, what about the I plus on Im? Okay. This can be obtained in general, and I am going to give you the relation, namely it is I minus m into I plus m plus 1 square root I m plus 1. Okay. And likewise, I minus on Im is square root of I plus m and I minus m plus 1 I m minus 1. One way to remember this combination, whether it is a plus or minus in the first term, is to recall the fact that I plus on I, the highest state, is 0, and I minus on the lowest state, I minus I, is 0. This is the m value. These are the m values. Okay. So, m takes the value minus I plus 1, I minus 1 I. This is what you had. For a spin a half, it was very easy. This was a minus a half and this was a plus a half. There were only two states because minus I plus 1 stopped with I. Therefore, for a spin a half system, the I plus on II was essentially I plus on half half, that was 0, and you can see that right away, that I minus m ensures that m never exceeds I, m never exceeds I. Therefore, if you were to arrange the states in some ladder form, then in the ladder the lowest is I minus I and the highest is I, and the I plus operator takes it up and the I minus operator takes it down, but there is nothing below the lowest and there is nothing above the highest. So, it is easy to remember that. The moment you remember I minus m, you can immediately recall that it is I plus m plus 1. So, some way of mnemonic form to recall and remember important relations. Okay. Therefore, if you were to write on Ix, the action of Ix on Im, it is 1 by 2 of I plus I minus on Im. Okay. Thus, the answer would be 1 by 2 square root of I minus m times I plus m plus 1 with the state I m plus 1 and I minus giving you plus square root of I plus m I minus m plus 1 on the state I m minus 1. Okay. That is the matrix, that is the action of the operator on the state Im. Therefore, the state Im is not an eigenfunction of the operator Ix, the same way like the Pauli spin matrix, that is the Ix was not giving you the eigenvalue for the alpha state or the beta state. it gives you im plus 1 or im minus 1. So, let me just highlight that alone. So, the state im when it is acted on by ix gives you im plus 1 or im minus 1. Therefore, recalling that the states im and im prime are orthogonal delta m prime, it is immediately possible for us to write that if I write im prime ix on im, I will get the result, namely delta m prime square root of I minus m, I plus m plus 1, and here the m prime is what? The m here is m plus 1. M plus 1 m prime, because m prime has to be equal to this in order for ix on im, which gives you im plus 1, to be non-zero. Therefore, m prime so this im prime will recover this im plus 1 on the action of ix on im, provided this m prime is equal to m plus 1. That is what this is, the part. Now, what about this term? This term tells you that if m prime, let me use a different label, if m prime were equal to m minus 1, then m minus 1 will be recovered. So, the second term that you will get is delta m minus 1 m prime square root of I plus m I minus m plus 1. So, the matrix elements of this quantity ix, if I have to write the general operator im prime ix im, the matrix elements of this operator ix are non-zero, provided m prime is equal to m plus or minus 1. Those are the only two possibilities. If m prime is equal to m plus 1, this is the matrix element. If m prime is equal to m minus 1, this is the matrix element. Therefore, if you write this in the matrix notation, generally for example, let us write this for spin 1. If we write this for spin 1, the im will be 1 1, 1 0, 1 minus 1, and the raw states are 1 0, 1 minus 1. Now, this element is 1 1 ix 1 1. This is 0 because the two states are identical. This element is 1 1 ix 1 0. This is not 0 because m prime is equal to m minus 1, because there is a plus component of this which will raise 0 to 1, and therefore, this element is non-zero. But on the other hand, this will be 0 because here m prime, this minus 1 is not m plus minus 1, but it is actually 2 off. So, this is 0, this is non-zero, and likewise you have 1 0 ix 1 1, this is non-zero, 1 0 ix 1 0, this is 0, 1 0 ix 1 minus 1, this is non-zero, and likewise 1 minus 1 ix 1 1, this is 0, this is 0, this is non-zero, 1 minus 1 ix 1 0, and then the diagonal element 1 minus 1 ix 1 minus 1, this is 0. So, for a spin 1, if you calculate these things using that formula, you must get the operator representation, the matrix representation for the operator will turn out to be 1 by root 2, 0, 1, 0, 1, 0, 1, 0, 1, 0. This 1 by root 2 is basically 1 by 2, and the matrix elements that you calculate will all be root 2, 0, root 2, 0, root 2. So, I have cancelled the root 2 to give you this. Okay. This is what you will get. This is what you will get from this calculation. Okay. So, this is for Ix. What about Iy? Iy is minus I by 2, I plus minus I minus. Therefore, you can see that I m plus 1, let me write, because we know it is going to be only one or the other. Iy, Im will be minus I by 2, Im plus 1, I plus on Im. The minus will bring it down to m minus 1, therefore, they are orthogonal to each other. And Im minus 1 on Iy, Im will be, there is a minus sign here, so it will be plus I by 2, Im minus 1, I minus on Im. I minus on Im lowers it to one value down, and therefore, the normalization property of the states Im is 1. That takes care of, and therefore, you can write the same thing as Im minus 1, Im minus 1, that is also 1, any value of m which is the same on both the Kettenbrough states. So, given this, if we can write the Iy operator as 1 by or minus I by root 2. Okay. Now, let us see this. This is the first element is 0 because it is diagonal. You can write all these things are 0, and the 2 off diagonal, they are also 0. Therefore, what you have is this element is 1 1 I plus 1 0. So, that corresponds to this type of matrix element. 1 1 m is 0, then you have that, and therefore, the corresponding value will be there is a minus I by root 2 is already taken. Therefore, this is 1, this will be 1, this will be minus 1, this will be minus 1. Okay. So, this is the representation for you can calculate it based on this formula. Okay. There will be some tutorial examples for you to do that, but try to follow this formula, namely the very first one, this formula. Keep this in mind. Okay. These are the properties of spin-1 operators. However, for spin-1 or any higher spin angular momentum, we cannot write Ix Iy plus Iy Ix is not 0. Okay. And for any spin including half, the relation is Ix Iy minus Iy Ix is always Iz, always, no matter whether the I corresponds to spin a half or spin 1 or 3 halves and so on. If the system is a spin 3 half system, chlorine nucleus, chlorine 35 nucleus has a nuclear magnetic moment that corresponds to a spin 3 half system. For spin 3 halves, we will have 4 basis functions. Im will be 3 by 2, 3 by 2, I minus 1 will be 1 by 2, then you will have 3 by 2 minus 1 by 2 and 3 by 2 minus 3 by 2. So, there are 4 states. And so, the spin 3 half representation, the matrix representation for Ix, Iy and Iz for a spin 3 half system is a 4 by 4 matrix. Okay. And likewise for any spin I, it is a 2i plus 1 by 2i plus 1 matrices. So, these are properties of the spin half systems, arbitrary spin I systems. Okay. Now, we will get into an extremely important problem in both spectroscopy and in quantum chemistry, namely the interaction between two spin half systems. The interaction between two spin half systems in quantum chemistry is of course extremely important because we deal with electrons, many electron systems, and in nuclei we deal with the nuclear magnetic resonance, electron paramagnetic resonance, NMR spectroscopy, EPR spectroscopy, and anywhere where the orbital angular momentum of anywhere two spin half systems interact. Orbital angular momentum is an integer angular momentum. We are only talking about two spin half systems. So, these are all areas where the interactions have to be studied. Okay. And since the whole concept requires what is called the spin state representation for a two spin system, it is like what was introduced earlier in one of the mathematics lecture notes as the direct product of two single component systems, and let me do that in the next lecture. We will stop here in concluding that it is possible for us to write matrix representation for all the operators Ix, Iy, Iz and a host of others, namely Ix square, Iy square, Iz square, Ix, Iy, Ix, Iz, Iy, Iz, all these operators for any I. Okay. So, we will stop here as the component for single spin systems, and in the next lecture let me start looking at the interaction between the two spin half systems from the background of what is meant by a two spin half states, what is meant by the operator representation for two spin half states, and so on. So, until then, thank you very much.